Hello, and welcome to today's webinar on Master Hardware Designs to Prevent RF Interference. This is the second part of the webinar series on RF interference. Our first webinar on the topic was held in last February. Today, we will do a deeper dive into the topic, and the aim is for you to understand how to get your RF front-end circuits right from the beginning. My name is Karin Steinhauser, and I will be moderating the webinar in this session. Before we begin, there are some housekeeping points. This webinar is being recorded and it will be sent to you automatically after the webinar ends. If you look into the handouts section on the webinar control panel now, you will find the presentation in PDF form. Of course, we would love to hear from you, so go ahead, write any comments or questions in the webinar control panel, and we will do our best to get back to you during the live Q&A at the end of this session. Moving on to the program of this webinar. In today's session, we will be covering an introduction of the RF interference topic. Then we will go into the RF front-end design targets, GNSS performance, immunity to RF interference. Then we will go to the topic of typical RF front-end circuits, and Rico will go into the calculation examples, GNSS performance, immunity to RF interference, and we'll close it off with real-life product examples with the Neo M9N and the Max M10S. Finally, we'll close it off with a live Q&A session. For those of you just joining us, welcome to the webinar on Master Hardware Designs to Prevent RF Interference. Get your RF front-end circuits right from the beginning. And now I would like to introduce you to today's presenters. Matthias Vetter is a product manager expert in RF and GNSS and is a specialist in sensor-enhanced positioning and meter-level positioning technology at u-blox. He has 7 years of product management in RF and GNSS, and specifically in the markets transportation and mobile communication. Riku Mekkinen is manager in standard precision GNSS and has a doctor title in electronics and electrical engineering from the University of Technology in Tampere. He has over 15 years of experience in computational electromagnetics and RF modeling. And he worked at Nokia Microsoft for 3 years in OTA test development, antenna design. Without further ado, I hand the floor over to Matthias.
Thank you, Karin. Hello, everyone. This is Matthias speaking. So my part will be pretty small today. Just want to make sure that the expectations are set correctly and everybody knows what we're going to talk about and what not, obviously. And I'm really glad that Riku is joining us today. Hi, Riku.
Hi, Matthias.
So let's go to the next slide. Let's start with the basics. So we all know the intention of a GNSS receiver is to collect satellite signals and to output a PVT solution, providing position, velocity, and time. So far the theory, I think that's all well understood. Now, there are interfering signals that come from the outside as cellular transmitter, but also from the inside the box where the GNSS receiver is installed. So, Riku, from your experience, are you involved in these RF interference topics with customers?
Yes, sometimes we get questions from chip customers who are designing their RF front end, also from module customers who are trying to decide which product is right for them. And of course, if something doesn't work out very well, then we are also going to get to know about it.
So if something doesn't work out, and I guess that's always when something is already built, that it doesn't work out, so either the prototype or already when the product is finished. So it looks like this is adding some costs to R&D. It's also adding some development time, having to do loops, having to do a redesign, and also it could affect product quality if the design is not done right. It could not reach the quality level expected. I somehow like to say that today's world is getting noisier than 20 years ago. And it seems the same is true for GNSS receivers. Do you agree?
Yeah, so there has always been interference in electronics systems, but with the higher level of integration nowadays and also more connectivity, additional radios in place. So yes, maybe it's getting more severe.
So yeah, I think this miniaturization trend is really a key one here, and the ease of use. Customers want to have a smooth experience. So our customers are integrating a lot of RF technology besides the GNSS. So it seems RF interference topics do become more critical. So let's look at the poll results from last time webinar, and here it's very good to see that the main customer problem around RF interference are board design issues and wireless transmitters. So these two parts. And today we will really focus on the wireless transmitter part, deep dive into that one. Then we see as well many customers are suffering from RF interference, and quite a few of them are not really sure what they should do about it. So we have a lot of registrants today. I'm really happy, and let's move on here. Well, it's difficult to flip. Okay, then I think it's very important to categorize the sources of RF interference to make it clear that there is intentional RF interference, so jamming and spoofing, where someone really wants to have some attack on the system. And there's unintentional RF interference, where it just happens because of the complexity we were talking about, the wireless transmitters, but also in-band frequencies can be affected from the digital electronics, analog electronics inside the box. And just to set the stage correctly here, today is really about the out-of-band interference and the wireless transmitters. And then we might do a next webinar really going deeper into the in-band interference mitigation if there is interest for that. So I don't want to say anything more. Let's move on and handing over to Karin for the first poll.
Thank you, Matthias, and thank you everyone for joining this webinar. So it's poll time, and I will in a moment pull it up, and I request you to please give the best answer that fits to your situation. So the first question is, what kind of designs are you working on? The first answer is module, second chip, or both, or none. I'm simply interested in the topic. I see the answers coming in. Thank you. Let me give a few moments for the rest of you to hand in your answers. All right, closing it off now. 3, 2, 1. And I will share the results. So the results show that 45% of you are working on modules and 7% on chips, and 24% say both, and about the same say you're just interested in the topic. This is very interesting results that most of you are working on modules, and I think this will be very valuable for us moving forward when we also do the next series. So now I will hand the word over to Riku. I will give you the control.
Hey, thank you, Karin. Hello, everybody. Riku here. So let's now have a few words about RF front-end design. Do I have control already? Trying to change the slide. Okay. On RF interference, so any of the sources mentioned here are relevant, but the main focus is on other onboard radios in the design. And the coupling typically happens through the GNSS antenna, where it's then conducted into the GNSS receiver input. And the impact can be anything from no impact to a complete loss of reception. The severity of the interference depends on the power level, frequency, modulation, bandwidth, repetition rate, and so forth. So it's up to the signal. We can divide the interference into in-band and out-of-band interference. The in-band interference we cannot address with the RF front-end design. Instead, we must address that at system level. We would use the mixed signal design concepts and clever component and antenna placement. And the idea there is to suppress the generation of the interference or mitigate its propagation. The out-of-band interference, this we can address with the RF front-end design. Typically, we use filtering, 1 or 2 SAW filters, depending on the application, to achieve this. From technical point of view, there are 2 main design targets. One is GNSS performance. We want to maximize the receiver sensitivity, and this we achieve by minimizing the system noise figure for the RF chain. On the other hand, we need to meet the immunity requirements, so we need to sufficiently suppress the out-of-band interference. And these 2 design targets are conflicting. It's not possible to optimize both at the same time, so one needs to make a trade-off. Also, there are other factors like the cost, size, and the power consumption of the circuit, so that adds another trade-off. About GNSS performance, the figure of merit here is the system noise figure. This is the total noise figure for the RF chain, and this is what we minimize for best performance. The system noise figure is the cascaded noise factor given in dBs. And this has direct impact on the signal-to-noise ratio and the sensitivity of the receiver, and therefore also to time to first fix. And for example, if the system noise figure increases by 3 dBs, then the signal-to-noise ratio and the receiver sensitivity, that will reduce by 3 dBs. So there's direct impact. The cascaded noise factor is the noise factor for a system consisting of multiple stages. In the picture on the right, you see a RF circuit with a SAW LNA SAW and the receiver itself. The F and G are the noise factor and gain for each stage given in linear units. And to calculate the cascaded noise factor, we use the Freeze formula that is shown on the left bottom there. And as we can see from the equation, the noise factor is dominated by the first stage. So any loss before the amplifier, in this case coming from the SAW filter, will increase the noise factor. With sufficiently high gain, the subsequent stages have a lesser impact. And this is because, as we see from the equation, the noise contribution from the subsequent stages is divided by the gain from the previous stages. The other target is immunity, and at the receiver end, we have immunity limit. This is the maximum RF power that is allowed at the receiver input that results in no degradation in performance. And if we are close to this limit or exceed it, then we need to verify that the performance is not degraded or that it is at an acceptable level. On the right-hand side, we see a graph for the immunity limit for our M9140 chip. On the x-axis, we have frequency from 400 to 3200 megahertz, and on the y-axis, we have the RF power given in dBms. And as we can see, as we move away from the in-band, the immunity typically increases, but there are certain narrow frequency bands where the immunity is reduced. And this is because the external interfering signal interacts with the internal signals and structures in the receiver. So there can be some intermodulation products that land at the GNSS frequency, and therefore the sensitivity is reduced. On the other side, we have the power coupled into the system. For a cellular radio or other radio system, we can estimate this from the maximum transmission power of the radio and then the isolation between the antennas. And the isolation between the antennas we can determine by simulations or making a simple test board. In the picture below, we have a test board. It should be the same dimensions as the final design with the same antenna placement, and then we can simply connect cables to the antenna terminals and measure the S21 with the VNA. And there is a good starting point for the antenna isolation in the design. For other interference sources, then also some prototyping might be needed to estimate the interference levels. So we had at one end the immunity limit of the receiver, at the other end the interfering power coupled into the GNSS antenna. Here are the most typical RF front-end circuits that we put in between to try to make everything work. On the left, we have LNA SAW. It has LNA first, so this is the design for best performance. But because of this unprotected LNA upfront, this is only suitable for designs that have very low interference levels. In the middle, we have SAW LNA. This is a general robust solution that is used for most applications. Here we have the SAW filter upfront protecting the LNA, and therefore we can allow interference in the system. On the right, we have SAW LNA SAW. With two SAW filters, we get very high out-of-band rejection, and that makes this circuit very common in designs with cellular radio. In this webinar, we are mainly discussing at high level, block level, but here's just an example of a real world RF front-end circuit. So basically this is the SAW LNA circuit, but there's some more stuff in it as well. On the right hand side, we have the input, the RF input for the GNSS receiver. And if we move to the left, we first have the matching network to match the input impedance. Then we have a DC block to prevent any DC bias propagating between the components. Then we have the LNA, and in front of that we have the matching network, typically a series inductance. Then we have yet another DC block, finally the SAW filter, and there's an additional filter there, this band 13 notch. It's a narrow band filter for to prevent band 13 interference. This will provide some 15 dB additional attenuation at a very narrow band. And finally, toward the antenna, we again have a DC block. So this is just to give an idea that although we are talking about at block level, the actual design is a bit more complicated. Let's then move on to some simple calculation examples. We are going to do simple calculation for the system noise figure and out-of-band immunity at two selected frequencies. And for those calculations, I have selected components that are used in the examples, and the values here, they are taken from real components, but I have rounded up the numbers a bit to make them nice. We have here LNA, SAW filter, and the GNSS receiver. For the LNA at in-band, the most relevant parameters are the gain and the noise figure. At outband, gain is also important because this reduces the immunity, because it amplifies also the interference. And the other very relevant parameter is the compression point. If this power level is exceeded at LNA input, it's driven in compression, so gain reduces and therefore the CNO of the signal will reduce, so that will have a negative impact. We need to stay below that value. For the SAW filter, the relevant parameter is insertion loss. At in-band, it's typically from 1 to 3 dBs. Here we have 2. And at outband, very high insertion loss, 45 or even 50 dBs. For the receiver, this is the noise figure for the M9140 chip. So we have 5 dBs. And at outband, we have the immunity limit from the curve shown before. And these values we are using in the noise figure and immunity calculations. Let's first look at the immunity GNSS performance. So the system noise figure, the relevant component values are copied on the left. And let's do the example for the SAW LNA circuit. On the right-hand side, we have the freeze formula. And here F1 and G1, they are the noise factor and gain for the SAW filter. F2 and G2 are the same for LNA. And finally, F3, we have the noise factor for the GNSS receiver. The component parameters are typically given in dBs, and for the freeze formula, we need to use linear units. So in the table on the left, we have the noise figure and gain in dBs. Then in the middle, those have been converted in linear units. And on the right, we then have the noise figure. And on the first row with red numbers, the insertion loss of the SAW filter is 2 dBs. So that means it has 2 dB noise figure and minus 2 dB gain. And at the end of this row, we have the noise figure of this circuit after the SAW filter. On the second line, we have the LNA. Noise figure is 1 dB, gain is 17 dBs. And at the end, we have the noise figure after the LNA. And on the last row, we have the GNSS receiver, noise figure of 5. And at the end of this line, we have the system noise figure, which is the total noise figure for the RF chain. And as we can see, any loss in front of the amplifier directly contributes to the noise figure. So basically, the noise figure of this circuit consists of the insertion loss of the SAW filter and the noise figure of the LNA. The receiver noise figure has little impact because there's an amplifier with relatively high gain in front of it, so that contribution is not very high. Here we have the values calculated for the 3 different circuits using these example components: LNA SAW, SAW LNA, and SAW LNA SAW. The numbers are shown here in case somebody wants to do the calculation, so you can compare your results to mine. But let's just wrap up the results from this slide. So for LNA SAW, we have the lowest noise figure because we have the amplifier first. So this is certainly the design for best performance. When we have the SAW filter in front of the LNA, the noise figure is of the order of 3 dBs. This is because this is directly contributing to the system noise figure. For the SAW LNA SAW, the SAW filter after the LNA increases the total noise figure very little because the gain of the LNA mitigates most of the contribution. But in short, LNA first, good noise figure, SAW filter first, some reduction or increase actually. Okay, let's then move on to immunity calculation. So here's an example where we have a cellular radio LTE signal. We consider two example uplink frequencies, 915 and 1880 megahertz. So first we need to estimate the power coupled to the GNSS antenna. So on the first line in the table, we have the transmission power for the LTE, which is 23 dBms. Then I have made up a number for antenna isolation. 10 dBs is a typical value. Let's say I measured it with my test board I built like on a earlier slide. This value can be even 6 dBs for a very small design, but typically you see something between 10 to 20 dBs maybe. But with this antenna isolation and the LTE transmission power, we have 13 dBms coupled into the GNSS antenna input. On the right-hand side, we have the GNSS receiver, which has a certain immunity limit, and the front-end circuit we put in between should fulfill the immunity limit of the GNSS receiver for this coupled power level. So we can simply calculate our design target for immunity. We need 38 and 43 dBs attenuation at those two frequencies. There's one additional thing to consider. If we have an LNA in the front-end circuit, we also need to make sure that the input of the LNA is protected. And for this LNA, we had the compression point of -12 dBms, meaning that we should not exceed this power level to avoid driving the LNA in saturation. So with the 13 dBms coupled to the antenna and -12 dBm compression point for the LNA, we need 25 dBs attenuation in front of the LNA. So this is an additional constraint. Let's then move on to actual immunity limit or immunity calculation for the GNSS receiver input. For LNA SAW, we just calculated that we have 13 dBms power coupled to the GNSS antenna, while the LNA input allows -12 dBms. So if they are directly connected together, this design is not feasible for this example. So let's focus on the SAW LNA and SAW LNA SAW. The calculation is shown in the two tables there. On the left, we have the frequency, the two frequencies we selected. Then we have the insertion loss in red for the first SAW filter in front of the LNA. Then we have the LNA gain, which reduces the immunity. That's in blue. And then in yellow color, we have the insertion loss for the SAW filter following the LNA. And from these values, we can calculate the out-of-band rejection for these two circuits. For SAW LNA, we have 45 dBs at 915 and 38 dBs at 1880 megahertz. And these values we compare to the design target, which was how much rejection is needed between the antenna and the receiver input. So we see that at 915 we are okay, but at 1880 we do not meet this design target. At this point, we need to test. we need to verify if there is degradation and if it is at an acceptable level. So we need to make test and decide. For the SAW LNA SAW, because we have 2 SAW filters there, the out-of-band rejection is very high. We have 90 dBs and 88 dBs, and this is clearly exceeds the design target. This is actually overkill for this design. So now we can consider maybe selecting some other SAW filters that may have lower out-of-band rejection. Those components also typically have lower insertion loss at in-band, so we might change the type of the SAW filter, and then we might still meet the design target for immunity, but at the same time we might be able to reduce the system noise figure. Let's then have a look at some u-blox products. Relatively new module, Neo M9N. This basically has the SAW LNA structure with this additional band 13 protection. This makes this product a robust solution for most applications. And for applications using the band 13, this has this additional protection integrated in it. In the middle, we have a new product, Max M10S. This is basically LNA SAW structure because the notch filter we have placed in front of the LNA is invisible at GNSS frequencies. So this makes this the highest sensitivity RF circuit we can select. But this can be used only for designs that have relatively low interference levels. Unless, the picture on the right, if we add an external SAW filter in front of the module, then we have SAW LNA SAW, which gives the highest immunity. And we also have this additional band 13 rejection there. And the external SAW filter that can be selected based on the design to optimize the immunity versus system noise figure. So this makes this a very nice product. It can offer highest sensitivity and with very minor addition, highest immunity. Okay, let's wrap up then. I have just collected in the table the calculations with these example components. From the technical point of view, we had design targets for performance and immunity, and also other targets coming from cost, size, and power consumption. And the designer's task is to select the right RF front-end circuit, consider if any additional filtering is needed, and then select right components. We only had one set of components as an example, but the designer would do the calculations for different components and different front-end circuits to find the best solution for the application.
Okay, thank you very much, Riku. Now it's poll time to keep you all engaged. So the next question will be pulled up onto your screens. Please go ahead and click the answer that fits best for you. If you already had RF interference issues, where were they? The first answer would be in band, second would be out of band, or the last option, I don't know. See the answers coming in. All right, give you a few moments and I will close it off and share the results. So 23% of you have said most of the RF interference is coming from the in band, and then 37% of you say out of band, and the majority say you don't know. Thank you very much for these results and for sharing your thoughts and your experiences. Now we will close it off with a few slides by Rico on the in-band interference preview.
Yes, so this was not the topic of this webinar, but let's have a short preview on this. The in-band interference, as we said, we cannot address this with RF front-end design. This is because we cannot filter out the frequency band we are interested in. Instead, this must be addressed at system level. Like I said, eliminate the interference at its source and, if not possible, mitigate the propagation. And here the tools we have is the frequency plan to avoid harmonics falling at GNSS frequency. For example, selecting the DC-DC converter clocks so that harmonics do not fall directly at GNSS. Grounding principles, antenna and component placement, shielding, whatever. So this type of layout, routing, those kind of approaches. In the picture on the right, there's a little example. The GNSS antenna is on one side of the design and all the electronics is on the other side. And the ground plane below the antenna shields it from any interference coming from the other side of the design. Of course, if you need to put something else on the same side as the GNSS antenna, then component placement, antenna placement, shielding, routing at inner layers, those kind of things need to be done. In our latest products, M9 and M10 platforms, we have a nice tool to monitor the in-band RF interference. So there is a message, UBX1 and a view in our U-Center support tool that shows what the message has in it. And what it has is the in-band frequency spectrum of the signal. There's a picture of that view on the right, and you can see the spectrum there. So this is a clean, nice spectrum and doesn't have any significant interference in it. But this tool can be used during product development, prototyping, to first of all observe if you have in-band interference and then try to identify the source for the interference. For example, you can turn on and off different parts of the design and see when the interference is there and when not. Also, the frequency of the interference spike might tell where it's coming from. And of course, if some modifications are done, one can see if they have any effect on the interference. But using this tool, it's important to note that there's interference in every system. And if you see some spikes there, that is very common and it might not be a problem. So in addition to this tool, you also need to look at the signal to noise ratio of the GNSS signals. Only if there is some degradation in CNO, this interference is significant and needs to be addressed. Otherwise, you can be completely okay. I think this is all from my side.
Yes, thank you, Rico. Okay, so let's have a last poll for this session, and it will be popping up right now. Would you be interested in a part 3 webinar on the mitigation of out-of-band interference issues? So please go ahead, click on your screens, give us your answers, and we will respond then perhaps with a part 3 series.
We made a mistake here. It should mean
Oh,
in-band interference issues, obviously. We talked about out-of-band just now. So we want to know about if you're interested to know about the mitigation of in-band interference issues. Sorry about that.
thank you, Matthias, for correcting that. All right, then we'll close it off now. 3, 2, 1. And we'll share the results. So 88% of you are interested in having a follow-up webinar on mitigating in-band interference. And 13% of you are not sure yet. Thank you very much for your answers, and sorry about that for the mistake, and we'll continue now. So if you are interested for more webinars, we have, as mentioned in the beginning, the part 1 of the Mitigate RF Interference series, what you need to know. Then we have Mastering GNSS Timing, what you need to know, part 1, and then Mastering GNSS Timing, what you need to know, part 2. And we also have a webinar on micromobility design challenges, how to stand out in a competitive market. All of these webinars and more you can find on our website under u-blox.com/webinar. And if you are interested on more resources on the topics of standard precision positioning, you can go and head over to our website, u-blox.com/M9 or M10. And we have a technology page specific on the complete solution on standard precision positioning or meter level positioning. Then we have also videos available on our YouTube channel. Here I'm mentioning the u-blox M10 that we just announced a month ago. It's the new low power meter level GNSS positioning platform. Then we also have a demo on anti-spoofing, which is quite a hot topic related to security with the u-blox F9 and M9. And we have also available to the blog posts and various materials on our website for the magazines. And you can find these materials on our u-blox.com/blog website or /downloads. So now, without further ado, we'll open up to the floor for a live Q&A session so that our experts can answer your questions that you have given in the chat. Let me open it up. Okay, yes, go ahead and write your questions. There's still time for that, for us to look through the questions and answer them one by one. So there's a first question that I would like to read out to you, Riku, so that you can answer. Can you tell a bit more about the immunity limit curve? What is the definition for the immunity limit and how is it measured? What is u-blox recommendation for immunity design targets?
Thank you. First of all, that curve was measured using an LTE type signal, 64 cam modulation and 10 megahertz bandwidth. It doesn't look very impressive, but behind it is actually a number of measurements. u-blox 9 supports 4 GNSS. So we have, with all 4 GNSS enabled, we have measured the immunity for each GNSS signal, GPS, Galileo, Beidou. And in addition to this, because the input bandwidth of the GNSS receiver depends on the GNSS signals enabled, we have in addition repeated the measurement for individual GNSS enabled. So there is a total of 8 measurements behind this. And this is then some fitted curve to consider all of these separate measurements. The criterion in the measurement is that when we observe 3 dB degradation in the CNO, then that is the measurement result. And of course, for this curve that is shown here, we have then added some buffer there. Regarding the u-blox recommendation, so we recommend that the design would be such that there is no degradation in performance. So this is the recommendation, but the choice is with the designer. The designer makes the trade-off and decides what is acceptable. But our recommendation is for no degradation.
Okay, thank you for answering this question. Next question is, can we see if there is out-of-band interference in our design using the RF spectrum analyzer in U-Center?
Yes, so the spectrum really shows the in-band. So it doesn't show what happens out of this, let's say, about 100 megahertz bandwidth. But there is also additional information in that view, and one is the gain of the internal gain of the receiver. And if there is RF power that is not visible at in-band, it still typically results in the internal gain to reduce to compensate for the additional power. So one can also observe the value for the internal gain inside the receiver to detect if there is something at outband. But in the spectrum itself, one doesn't see it.
All right, there's a next question from Frederick. Why is B13 notch so relevant?
It's only relevant for designs that have band 13. But yes, that's a good question. So the frequency band of band 13, it's below 800 megahertz. And the second harmonic lands exactly at the GNSS frequency. And if we have an LNA, either external one or the one that is inside the u-blox GNSS receiver, the input of the LNA, any active component, is always nonlinear. And if this signal comes at the LNA input, the nonlinearity of the input generates harmonic frequencies. And the second harmonic falls directly at the GNSS band. And that will then be impossible to remove afterwards. So this is the reason why typically the band 13 is more vulnerable to have interference problems.
A question from Tim. If using an external active antenna, presumably the LNA SAW versus SAW LNA question in the u-blox module is less critical because the performance is dominated by the LNA in the antenna and because the cascaded noise figure calculation losses between the antenna and module not that critical. Shall I repeat the question?
Okay, let me try if I understood it. So if you have an active antenna that has sufficiently high gain, then whatever follows doesn't really have that much impact on the total system noise figure. But of course, one needs to calculate if the gain is sufficient. So how much cable loss there is and what is then the noise figure of the following parts. So one may need to check that the gain is sufficiently high to cancel out whatever follows. But yeah, what was discussed here also applies to the active antenna. So whether it's LNA source or LNA, it has the same good and bad aspects.
Okay, Tim James, if that answered your question, please just give us a note in the chat or in the question console. Next question from Ingemar. GNSS is normally using an active antenna. Are they normally using SAW filters, etc.?
I would say that typically active antennas have a SAW filter up front and then the amplifier, and then there might be even additional stages. But yes, I would think so that most of them do have.
All right, so there are a few of you are asking about the slides of this webinar. They are now available in the handout section. Go on and head over to the console, webinar console, and there you will see under handout section the slide deck. Next question, I see that is quite a good one from Renee. Hello, Riku. What is your experience with SAW LNA antenna structure? Is the additional noise a critical factor or is it typically acceptable?
I didn't quite get the bottom of the question. What is being asked?
What is your experience with SAW LNA antenna structure? Is additional noise a critical factor? Or, okay, maybe something is missing there. Please reformulate your question if you can, Renee.
But maybe I can say that, first of all, very often, because of the immunity point of view, you must have the SAW filter up front. You cannot avoid it. And if you must have it, then it's then selecting the component that then provides the best, lowest insertion loss possible while still having sufficient out-of-band rejection. But if this SAW filter upfront is mandatory, then it must be there. It cannot be avoided. And if the question actually relates to that whether SAW LNA is sufficient or do you really need to add the additional SAW filter after the LNA to have no degradation, that's the trade-off. One needs to decide what is acceptable and what is not, and then select the circuit and the components accordingly. Unfortunately, I cannot say anything more.
Yes, she just wrote that answers her question. Perfect. And also Tim says, thank you. Your answer was fine. It confirms. So next question. Is the small dip in the immunity curve around 2,400 megahertz exactly at BLE frequencies? It's not entirely clear from the graph. In your experience, is it common to have severe BLE interference from an onboard transceiver?
So this graph is taken from the integration manual for the M9140 chip. Unfortunately, this version has not yet been released, but this will be there. And there is also an additional table showing at which frequencies those transition points are. So I don't remember exactly where that is. But yes, in general, also Wi-Fi or Bluetooth can interfere with the GNSS. So that also should be checked, just like cellular radio.
Okay, so there's still a question left if we can answer. Before we close off this webinar, please go ahead and ask your questions. We still have a minute. And I see that there is one question that just came in from Keys. It's concerning on page 20. Let me just go ahead and move the slides to that page. And he's asking that he doesn't fully understand the table at page 20. How is F and the gain determined, and how is NF determined?
For the SAW filter, so the only parameter is insertion loss, and any loss is directly proportional to the noise figure for that component having this loss. So the noise figure 2 dBs comes directly from the loss of that component. And the gain -2, because this is loss, so when the signal propagates through the SAW filter, it is attenuated. So therefore it has a negative gain. For the LNA, I think it's more straightforward. And the conversion from decibels to linear units, this is 10 to the power of the gain in dBs divided by 10. And that's the way you move on to the linear units, to the calculations to get F total. And there you do 10 log n to go back to the decibels.
Okay, there are quite a few questions still coming in. So from Oliver, there's a question. Are high linearity LNAs, high P1 dB, usually not used due to high current consumption and higher price points?
This is the trade-off. So if you have low power LNA, the linearity is often not as good as with a high power LNA. So if the LNA current consumption is something like 1.5, 2.2 milliamps, then often the linearity is not as good as with an LNA with 3 milliamp or higher current consumption. So it's a trade-off.
Great. So from Mr. Steinmetz, there's a question. Is there a receiver immunity diagram for the F9P available? Thank you.
I'm sorry, I have no idea because I work for standard precision products and this is a high precision product. So I don't know, but I will tell the guys that it would be appreciated if there was.
Yes, maybe we can have a webinar on high precision immunity.
I also checked, couldn't find it just easily. So maybe it's good to get in touch with us, with our technical team. And if you have some specific questions for specific frequencies, maybe they can answer this in an easy way.
All right. Thank you so much, everyone, for the questions. We have 2 minutes left, so unfortunately, we cannot go through more questions right now. However, we will definitely look into having a next series, next webinar in this topic. And thank you for engagement. I would like to just close off with this slide. If you are interested to know more, as Matthias also mentioned, please go ahead to our website. There is the contacts, our technical support contacts. Then there is a support form where you can also write your feedback and questions. Then there are the sales contacts. And of course, there are also lots of documentation available on our website. So thank you very much, everyone. I wish you a great rest of the day. We will send you a recording of this webinar, and also you can go on our website, u-blox.com/webinars to see when it's uploaded. Thank you very much. Take care. Bye.